So next we can move on to, having known that the internal generated voltage is determined by that, what are the actual parameters of the machine? So like, what is the equivalent circuit of the synchronous generator? So here we have, once again, a cross section of the synchronous generator, simplified as we had done initially in the past. So you have your stator and you have your rotor, simplified to 2 poles, and it is rotating at a speed of omega m. Okay, and because of that, it has a flux that has a value of Br, that is the magnetic field within the rotor. Okay, and then you have your internal generated voltage. But before we get to that, right, we need to look at, remember we've said we have 2 different things that we are looking at. I mentioned when we are looking at the output of our generator, what the load sees is a phase voltage, that is a terminal voltage that is available at the 3 or the 4, in the case of a star connected machine, terminals of our alternator. What voltage does the load see? We are giving it as terminal voltage V5. But we've mentioned that the internal generated voltage is given by EA. Now, what actually happens during the operation is that your internal generated voltage will not be equal to the terminal voltage. There is a difference between the 2 of them. So your internal will never be equal to your terminal voltage. Okay, internal generated voltage, what the windings in the armature are seeing; terminal voltage, what your potential load and output is seeing. Okay, so why is this the case? There are 4 factors that determine that. Number 1 is the shape of the poles. Okay, remember we mentioned when we are talking about the internal generated voltage, we've talked of the distribution, the pitch, the form factor, and so on and so forth. So those have an impact on how the terminal voltage will be passed on to the load. This is either you have salient poles or you have cylindrical poles. In most generators, in most practical applications of generators, you will tend to have salient poles. That is the ones that stick out, which you saw in the video, which you saw also in the photo. Let's show the photo again. So these are the salient poles that we are talking about, right? Each pole sticks out from the cylinder of the thing. They are not distributed along the rotor itself, right? For purposes of the discussion we are having, we will assume that all our generators in these calculations that we are doing have salient poles, and we will disregard the factor of cylindrical poles. Number 2, which is by far the biggest impact, you have armature reaction. Okay, and we will describe armature reaction shortly. Number 3, you have resistance of armature coils. Yeah, remember you have your internal generated voltage coming across from the stator, or from the rotor to the stator. The field is inducing some voltage within the windings of the armature, within the windings of the stator. Those windings are not perfect. They have a resistance in themselves. You know, all copper, all aluminum, whatever windings you're using will have a resistance. So that has an impact. There's a voltage drop between the internal generated voltage that you find and what is available at the terminal voltage. And finally, you also have self-inductance of the armature coils. So similarly, these two together, this is the impedance of the windings in the stator. Okay, so any equation between the two of them will have to factor in the impedance of the windings as well as the armature reaction. Type of poles, we have said we will assume salient, so that will not really come into play in our discussions as we look at the equivalent circuit. So let's look at the armature reaction. The armature reaction has the biggest impact on the difference between the two. So let's have a look at it. All right. So here is our cross section of our motor. Now let's assume the motor is running, the field winding is rotating within the space of the stator. So you have your rotor moving in this direction as per what you have. If you have your rotor moving in this direction with the magnetic field in the direction shown, which is that way, you will then have induced voltages in the directions that are shown. So if we assume these are coils or windings within the stator or within the armature, any current that would flow out of the screen in this section and would flow into the screen in these sections that are there in the lower half because of the action of the rotor. We went through this when we were looking at the principle of operation of a rotating magnetic field. It is the same thing that we have here. A rotating magnetic field cutting across conductors. As simple as that. All right. So what you have now is you have a rotating magnetic field that is interacting with the stator. So that field is given by BR. It is in this direction and it has a certain magnitude. All right. Now, because of the action of this magnetic field, we have now created an internal generated voltage within these windings, and we call it EA, which has a peak of EA max, right? So those two, because of the interaction of the field with the conductors, the stationary conductors, create now your internal magnetic or rather internal generated voltage. So what happens next? Let's add a load. When you add a load, you then have an internal current that is induced in the stator that has a certain flow. So let's call it IA, okay? It has a flow within the windings. So in addition to the voltage, you now have, when you have a load, you have a current that is flowing through the windings, right? Now, this current, depending on what the load is, let's assume we are running a bunch of motors. Let's say this is a lagging current that is flowing, okay? What you will find is your current IA, remember this is a rotating magnetic field. Because you have your current IA, you will then have, in turn, your IA will also start creating magnetic fields within because of the action of a current flowing inside a conductor. A current flowing inside a conductor sets up a magnetic field around it. Yeah. For purposes of this diagram, direction will be something like that. Okay. The net result of that is that you will have eventually another magnetic field that will a magnetic field, let me draw it this way, that will have a resultant, say, in that direction. Okay. Right. So let's say it's moving in that direction. And this magnetic field has been created by IA because IA in itself has created there's a current that's flowing through the conductors, and therefore there's a magnetic field that interacts with this magnetic field that is already there. So this one now is another magnetic field B, but it is because of the stator, right? The armature windings, the current that is flowing through the armature windings creates a magnetic field that is there. Now, what happened when we had a magnetic field within the rotor initially? It came with its own internal generated voltage. The same thing happens here. Yeah, you will now have a voltage that is created, but this is now an armature reaction voltage, and it is a voltage because of the stator, right? So E stator we call the armature reaction voltage. Okay, remember this is due to a lagging current because of the load that has been connected. It is drawing a current. There's a difference between those the current that is flowing and the voltage that created it. So now you have another field that is created, another magnetic field. So in the end, you now have, in this same space, you have your BR and you have your BS together within the same space. What then happens is you end up with a net field here, depending on the magnitude of the armature reaction, a net field which is the resultant of this. Okay, I've not drawn it to scale. Call it that. But you know, if you were to superimpose the net effect of that, if you add BS to here, the resultant is B net. Sorry, the scale was not very. Let me try and retroactively amend that. Okay, so let's say BS is that size. Okay, so our BS is here. And when it is, you find the resultant of the two, BR and BS, you have a net B or magnetic field that is distorted. Yeah, so you have a distorted field from what you originally had from the rotor that gives you B net. And what you find is that this B net comes with your own final voltage, which is V phi, which is the ultimate terminal voltage. Okay, and that is the gap between the two. Now, in addition to BS, of course, your current IA was generating the armature reaction voltage. It is creating your armature reaction voltage in the form of the magnetic field that is there. Remember that your IA is flowing through the armature coils. So you then have the interaction of the resistance and the self-inductance. So what we now end up with is you have all the components that are necessary, all the components that form part of the circuit of your the internal operations of your electrical machine or the synchronous generator. So what will eventually happen is you have E start, the voltage here, can be represented by an X, a certain inductance due to the armature reaction. All right, we represent it by an X there times the current IA, right? Because it interacts, it is due to IA and it interacts with the others. So when you put it as in terms of a voltage, you create this element that will be able to put it into the form of a voltage. So now you have your voltage V phi, which is given by EA plus E start, right? Because you have, remember that the V phi is the resultant of the net magnetic field, which is the initial magnetic field that you had plus the armature reaction voltage, or rather the field due to the armature reaction, right? So this then becomes EA minus JXIA. Okay. So if we want to now also include the impact of the resistance and the self-inductance of the coils, you then have an additional one. So this element is due to armature reaction It is the representation of armature reaction. You will also have to now subtract again a value JXAIA, where XA is the self inductance that we talked about of the armature coils. And in addition to that, you will also have to subtract X, not X, this is R, which is the resistance, RA times the current that you're flowing through the armature, which is the resistance of the windings. So having put all of that together, we are now in a position to indicate what is the actual representation of the internal generated voltage. So we have it as, if we take it to the other side and have your terminal voltage on this side, it can be V5 plus J times XIA plus J times XAIA plus again to IA. So now you then have all the components that you would need to create an equivalent circuit of your alternator or your synchronous generator. Now, for convenience, we tend to combine these two inductive elements, whereby we give them a value called the synchronous reactance. Synchronous reactance, which is equal to the sum of the two. Okay, so the reactance due to armature reaction and the reactance due to self-inductance of the windings themselves, right? So your final equation would look like EA equals V5 plus JXSIA plus RI. Or in other words, V5 is equal to EA minus JXSIA minus RAIA. So you have a circuit that looks something like this. So, of course, this is a three-phase machine. So this would be EA1, V51, and so on and so forth. So you would have actually three of these windings. Where you have EA1, EA2, and EA3. So you have three windings with all the elements that you are talking about, RA, and you have three phases, V5-3, right? So this is the armature side. To complete the circuit, we can indicate on the field side what are some of the elements that you have. Sorry for the roughness of that. So this would be RF, the resistance of the field windings. This would be XF, the inductance due to the field windings. And over here, we can have now an adjustment resistance that allows us now to play around with the value of the field current. Remember, we said that the amount of the internal generated voltage, EA, is directly proportional to IF, as well as the speed of rotation and, of course, the construction factors. So this IF is regulated using that resistance that you have there, right? Then you'll have, of course, a VF on that side. So this is essentially your equivalent circuit of the synchronous generator, okay? So at the same time, let's look at a couple of additional characteristics of the this electrical circuit that we have here. So let's take a look at one of these elements, yeah, so that we look at what do the phase diagrams look like? This is your very important equation. And that was your derivation. Okay, so we are all here together. Right, so the phase diagrams. Remember that we have two main voltages that we're looking at. We had our EA, the internal generated voltage, and you have your terminal voltage, the internal generated and the terminal voltage. So now let's take the terminal voltage to be our baseline. So that is your terminal voltage. Let's call it V5. Okay. We are assuming it is at 0 degrees angle, and we are assuming it is our baseline, which we will use to take the same. Now, if you have a load that has unity power factor, okay, so it is at the same power angle as your terminal voltage. So let's say it is just in parallel here. Let's call it IA at unity power factor, right? They are parallel to each other in the same direction. What happens to your other elements? So you have your current IA, let's indicate it here. So your current IA flowing through your entire circuit, assuming we add a load that looks like that, right? So you have IA flowing through, you have a terminal voltage which is seen across these points, and you have your load which we have added there, right? Internal generated voltage is our source. Now, the IA interacts with the RA, and you have a voltage drop in that point, okay? So this is IA, RA, okay? RA, or rather the resistance, does not alter the direction of the current. So you have IARA, which is your voltage there, can be added, and it will look like that, okay? So that is the potential drop due to this element RA. Potential drop due to JXS. Straight away you have your complex or your reactive element. So that means that your potential or the voltage drop that you have there will be at 90 degrees because of your J. It will be at 90 degrees to your current IA. So in that case, you draw it at 90 degrees and you have JIAXS, right? So remember we said your internal generated voltage EA is equal to the sum of the terminal voltage, the combined synchronous reactance times current, and the resistance times the current itself, which we have indicated here, okay? So the resultant EA is actually, if I can get a straight line here, it's actually from there to there. So you have EA being the resultant of all these elements. You have your terminal voltage, your resistance of the windings, and your synchronous reactance, the combined synchronous reactance. So there will be an angle between the internal generated voltage and the terminal voltage, right? This is for unity power factor. Note the magnitude that we are having. Let's say now we have our load. Instead of unity, it is at lagging power factor, right? Let me attempt to draw the voltage same way. That is V5. And you have now, because you have a lagging power factor, let's say our IA now has an angle to it, right? So they are now not parallel to each other the way the voltages, they initially at unity power factor they were. So now there is an angle. So what does that imply? It means that this element and this element now have a different direction. So the resistive element is in parallel to the direction of the current that was there. So it looks like that, in parallel to each other. Okay, let's assume that is parallel. The reactive element is still at 90 degrees. So we'll call it 90 degrees like that. Looks like that. So this is IARA and this is JIAXS, right? Let's call this IA1, IA2. This is EA1. So what you will see is a lagging power factor leads to an internal generated voltage that looks like that, right? So EA2, right? So straight away you can see when you compare the two, the magnitude of EA2 is much more, and also the angle at which it is being generated is less to compensate for the current changes that are there. So why do we take the terminal voltage as the fixed? Practically in the engineering scenarios, you would want a fixed terminal voltage. If your client is expecting 415 volts, you need to give them 415 volts. And that 415 volts would be the terminal voltage. As we said, what the load actually sees. Yeah, what the load will see is the terminal voltage. So you want it to be 415. So it means that if your load changes power factor, you have to vary your internal generated voltage accordingly. So if you have unity internal unity power factor, internal generated voltage is at this level. If you have a lagging power factor, internal generated voltage is at that level. So it means that you have to go back to your machine. In order to change the internal generated voltage, you have to now change your IF. So how do you do that? This is where now we have your resistance or your methods of changing the magnitude of the current that you have. Similarly with leading power factor, just for completeness, let's talk of leading power factor. Have your same terminal voltage, but in this case, IA3 now has a leading angle. So what does that mean? You will then have your IARA looking like that, IA3RA looking like that, and your IA2XS times J looking like that. And what that means is you now have EA3, which is actually at a much smaller, the magnitude or the length of this vector is much smaller than what we've seen. When you have a lagging power factor, you need more or higher voltage to produce the same terminal voltage. But when you have a load with a leading power factor, the terminal voltage, to retain the same terminal voltage, you can afford to reduce the magnitude of that. However, you have to have a much greater power angle between the two. Okay, so those are now factors that are needed. So now what you will see is when you have a lagging power factor, you need a large field current, and when you have a leading power factor, you don't need as much field current as we saw before. Okay, so that's essentially the equivalent circuit and the principles of operation of your synchronous generator. Let's wind up with an example. So you have a three-phase star-connected alternator that supplies a load of 10 megawatts, right? The load is lagging at 0.85, and we want a terminal voltage of 11 kV. Calculate the line value of EMF, so the internal generated voltage, which was EA. Okay, that's what we are. So EA is what we are trying to find. Okay. Right, so straight away, what is the output current that we have? The output current is equal to the power over √3 times terminal voltage times power factor. Okay, or let's call it cos phi times cos phi, right? And that is given by 10 times 10 to the power 6, which is 10 megawatts that we have here, divided by √3 times the time, which is 11,000, times the power factor. So let's do that. 10 exponential 6 divided by 3 times 11,000 times 0.85. Right, so that gives us 617.5 amps roughly. Okay, so that's the current that is now flowing through your circuit. Okay, now what is the phase value of the terminal voltage? Let's give phase phi. It is given by 11,000 divided by √3, which is 6,350.85 volt. What is our value of phi itself? So phi is cos inverse of 0.85. So it is 31 point, let's say 8 degrees. Okay, right, so we are moving that along. We want EA. So EA is given by V phi plus IA RA plus JIA XS. We can combine these two so that we have V phi plus IA into RA plus JXS. Okay, so EA is 6350 plus 617.5 at an angle of negative 31.8 degrees into 0.1 plus J 0.66. So that gives us 6350 plus 617.5 at an angle of negative 31.8 times 0.1 plus 0.66 I. And that is 6617.24 plus J313.83 volts. Convert that into that is equal to 6624.68 at an angle of 2.7. That's your EA. And the line value will be that times √3, which is 11,474.28, 2.7 degrees. And we can stop there. We will see you in the next lecture.